And very soon, in the next 2 weeks, we'll be able to make it. That's the big thing. Not a lot of robots actually. Oh yeah, well there's a walker right over there. So without further ado, we'll see if we can get it covered. There's also a nice little webcam. So this is what Iron Man sees throughout Imagine RIT.
It's a research platform for future use. So the current sensing in the robot will actually be used to help balance and make sure, so it'll be dynamic balancing. So if you come over and kind of push it, it would actually kind of lean like this, like adjust its weight. So that's actually
the end result is to build a very large robot as tall as your eyes, and actually give it a tour.
Yeah.
It's okay. Actually, that's a good question. Everyone needs to know. So downstairs there's a wonderful robotics lab called Mabel Robotics Lab. They helped sponsor this wonderful project. But throughout the time we get a lot of tours and everything at RIT. If any of you are RIT students, I'm sure you've been to tours. But as robotics students, we give the tour of the lab. Well, one of these days it's going to be like, all right, robot, you can handle that, and it'll talk and everything. Just give the tour. Obviously, we'll be there to help it, but we're just trying to get people interested in robotics and make it user friendly and integrated.
So right now it's actually voice activated. We're running a command that can take my voice input and it can do a number of commands based off of that. Point versus people, more time work. Robot. Action. Action. 2. Robot. Hello. It says hello, my name is TigerBot. It's kind of quiet, so I can't hear it well. Robot. Attack. Those are all the basic fun commands I gave it. It can also look left, up, or up, down, left, right. Robot. Robot. Robot.
The voice gets a little finicky because of the way we housed it. There should be a kind of insulated design around it, but based on the design we're using right now, it doesn't really fit too well.
Robot.
The microphone's kind of
So you don't have that power?
we can reset it. Do you want to try standing?
Yeah. Alright, so now we're going to demonstrate how it's able to stand on its own. What it'll do is, you and I can stand straight up like this. There's a lot of little teeny tiny muscle movements that go on while you're doing this. So in servos, those are actually very hard to recreate because your limbs aren't actually revolution joints. So what we have it do is gently crouch, and it'll kind of balance itself like this. It has an accelerometer, a gyro, and a compass. So the legs are also balanced using current sensing, much like James said. So if you push it, it'll sense a strain in the servos and it'll try to correct itself. If we know what servos are straining, we know what direction the force is pushing. So if I were to push myself backwards, your legs automatically do that. And that's what we're going to try to integrate. Any questions?
How far is the current sensing integrated so far? I see you have a board, you developed the board that measures, you go through it in A to D to measure.
Yes, so right now we only have the legs current sense because that's the primary strain on the servos. There's enough chips on here that we can use to actually do every limb for the time being. The arms don't really, we can twist the torso and everything, that's also current sense. But as far as limbs go, yeah, you can throw your arm, but it's not as pertinent as moving a leg.
How many joints are?
23 joints total. That's including the hands of freedom.
20 degrees of freedom. 20 degrees of freedom. But there's it's human joints. So there's but that's not joints. There's 3 joints in the leg, but the ankle has 2 degrees of freedom. Knee has 1. Hip has 3. So it's able to do pretty much every human motion. It might be a little off just because you don't have like a ball. You don't have a ball motor like on the hip. It's
You guys are done. We're at our presentation.
Okay. All right, we'll be right along. All right, so we shut the line. All right. Should just be whenever we're ready. Okay.
Nice. Ready to stand it? So right now we have to start from stand. The way when the servo if it's sitting down at all, or if something's blocking it, since it's servo's not in position, they'll take a very high current that can potentially fry the servo right now. So we
switch on the one on the right.
Nope, get it forward. These look awful.
Apparently not.
So we had it balancing. So right now we're not doing, well, we redid one of the limbs last night, so by redoing the limb, the actual position of the servo is slightly different.
You can reset it right now, though.
Send these forward. I don't have the Bible with me. The servo Bible.
Yes.
So I can't. Yes. Why should, fine.
These are 10 and 11. Remember, right? These are right. Want to do like a? Yeah, but it should be the same.
I can't.
I thought. Oh, you tried? Yeah. I promise to stand new videos for new videos of the stands. Alright. Here we go. I lied. Yeah, it doesn't count.
So once we actually get the dynamic balance, there's some play in these days, which when you're actually powering it, you can't tell about just where the servo position is. Each servo sits in that position. Once it starts playing the joints, you're slightly off that position. So with dynamic balancing, we have a gyroscope accelerometer in the chest, right around the center of balance. So once it starts shifting, we can tell there. If these servos are actually starting to drop over the bird, you can actually tell that there's a relationship. So you can be able to tell this is our future. So we're building a lot more parts. That's it for. I mean, that's all we have for now.
We'll have it walking in the next 2 weeks.
We're at week 20 out of 22 on this project. We're at week 20 out of 22 on this project. So, we started from scratch. Beginning of around that time.
So time was obviously a huge disadvantage, but it also got pretty good.
So
help me catch it. Yeah. Thank you very much. Thanks, guys. Yeah, just get these out.